Welcome to the DSCD podcast. I'm your host today, William Nagel. And today I have a very special guest, Danny Abramovitch. He's a system architect at Mass Spec Division at Agilent Technologies. Welcome, Danny.
Yeah, thanks, Willie. Good to be here. Thanks for the invite. And yeah, it was cool.
So you're definitely one of those guests that when I was on the team, it's like I'm going to start producing these podcasts. I'm like, okay, I got to get Danny on. He's perfect for this avenue and just a wonderful person to talk about dynamics and control and get have everybody excited about it. So I wanted to start by asking about if you could tell us a little bit about your background for any listeners who might not be familiar with who you are. So maybe where you studied, kind of what your industry career timeline has looked like so far.
Yeah, so it's funny because when I have to go through this, everybody in my family just rolls their eyes because they've heard it so often. People ask me, "Oh, where are you from?" And I say, "I was born in Canada. I grew up in Tuscaloosa, Alabama. Went to college at Clemson, spent a summer working for digital equipment in Nashua, New Hampshire before going to grad school at Stanford." And so that's a very compressed view of things. But basically, I think, my thesis was nothing to write home about. In my opinion, maybe everyone feels that way about their thesis. I certainly felt that way about mine. I got married in grad school, and my wife still had a year's work on her thesis. So basically, I went into local industry because the local colleges here are, Stanford and Berkeley. And they weren't calling me. To be fair, there's Santa Clara University and San Jose State. They weren't calling me either. So basically, I went into, I got a job at Ford Aerospace. It seemed like a nice, interesting place to go. And after about 10 months, I got an opportunity to go to HP Labs, Hewlett-Packard Labs. And back in the day, that was a really cool industrial place to work at. And so one of the things that I learned, though, because of my stint at Ford Aerospace, and Ford doesn't do aerospace anymore. The part of it that did part of it is now in Lockheed, and part of it is in Loral Space Systems stuff. But anyway, at that time, one of my coworkers, who I'm still in touch with, a great guy, he walks into my office one day and he says, "You're a controls person. How would you analyze a nonlinear phase lock loop?" And I just had this blank look on my face going, "What's a phase lock loop?" Right? Because, if you're a mechatronics, but you might not have heard of it, right? And so Dan Whitmer, I will give him a shout out because that conversation was very formative to my career. So Dan explained how, phase lock loops work, the basics of it, very patiently and everything. And I said something like knee-jerk, like, "Oh, I guess I'd use Lyapunov redesign," right? And it turns out that when I had that interview at HP Labs, I gave the talk based on that conversation, right? So it was incredibly useful. But the other thing is because I learned about phase lock loops, it's actually sort of run through my career. So there's this underlying thing that what I learned from phase lock loops that shows up in a lot of different problems, and I'll probably reference it again. So, but the origin story of that is, back in the Ford Aerospace days. And I went to work at HP Labs, and back then the group was the storage technologies department. And what we were working on, the group I got hired into, was to do optical recording. And back then people were trying to replace magnetic hard disk drives with optical drives because you can get tremendous areal density with the optical drives, but you can't solve the problem of basically the volumetric density. They could never quite solve it. So, but the areal density was fantastic. And so there's this whole stuff about how to do rewritable and stuff. And because people wanted to use a rotary actuator, it got me into doing MIMO control type stuff. And I had to build a test system to do that. And that took a long time because nothing that I wanted to do existed. Did everything I told my bosses it would do, and it wasn't enough. It's basically, it didn't do any of the things that you needed to do. I got it to where I could do all the stuff that I thought I needed to do from grad school. And that wasn't enough to solve these, mechatronic problems, because with these high sample rate systems and their, high frequency type dynamics, they're often lightly damped. A lot of what we learned basically tended to fall on its face. And I didn't realize it back then because I was fresh out of grad school. And so I basically struggled with, why isn't this working? Why can't I do the things that I know how to do by hand? Why doesn't it do it automatically? And so, a lot of time sort of over the years has been the same theme of, why does this not work, right? And trying to fix it, right? Figure that out. But then after a while, that project kind of went away, and then I was working on magnetic hard disks. And we did this thing, got a few interesting papers out of that, including something we really thought would change the way the division did their work, which was a thing we called Pez Pareto, which was looking at the error signals and decomposing them in terms of all their sources.
Mhm.
And that was relatively, well, we weren't going to publish it, but then HP got out of the disk drive business. So it's like, okay, well, can we publish it, right? And for about a decade after that, it was 1997 ACC in Albuquerque. And Terrell Hurst and I gave like 3 talks there, and people were like really jazzed about it. And for about 10 years, people were talking about, back then the disk drive companies came to ACCs, they would talk about Pez Pareto quite often. But it's basically this way of decomposing noise and looking at the primary sources. And it all drew from Gunter Stein's Respect the Unstable talk, which I got to see in person. Like, so it's like Woodstock for like
Oh,
control
wow.
engineers, right? But basically, Gunter Stein gave the inaugural Bodie lecture at a CDC. And I remember Rick Ehrlich and I were sitting, he's still working on disk drives, by the way. Rick Ehrlich and I were like sitting in the 10th row of this thing. And it was this thing where you like, they're listening to this guy who, like, he works at Honeywell and the other half of his time he spends at MIT. So, pretty interesting character. And he's talking about not just control theory, but the applications and the things, the theory that like really gets to you. And he's basically describing Bodie's integral theorem and why, if you don't pay attention to it, you're going to be in a lot of trouble. And so Pez Pareto came out of this thing where we were trying to figure out these primary limitations for disk drives. And I couldn't get this picture that Gunter had presented out of my head, this dude shoveling dirt, basically, and that's the sensitivity function. And his whole idea was that dirt was incompressible, and just like the sensitivity was incompressible, right? You could move it around, but it didn't go away. And so you had to learn about that. And it was like, there's something about this, right? And eventually I had this like revelation that this was all closed loop. And if you wanted to look at the noises, you had to like open the loop and make it look at the open loop noise sources. So that's a long thing, but it ended up being Pez Pareto, which was a lot of fun to do because you kind of figured out this is what really affects the system, right? And back then, everybody was arguing about how many bits you needed in your ADC. And it turns out that if you did the strata of the noise, like the ADC was like the least important thing in there. And then there was the DAC, and then there's a power amplifier, and then you got to the airflow banging the arms around because you have these spinning discs, right? And these arms are floating on an air cushion, and they're not designed to be overly aerodynamic, right? So Terrell, who was a pilot, he said, he's like, I'm going to make these things into like good wing, right? There's gonna, it's not going to be this
Right.
hockey puck floating around anymore. It's going to and so he started working on that. Well, the other main component was the position sensing noise, the noise that you got trying to sense, the error, and that went right, sensor noise goes right through. So it's fundamental control stuff. And you could just, by doing coherent demodulation, doing a better job of how you picked up the signals, you could knock half of that off right away. So we published that, and of course, HP got out of the business, and we went on and did some more optical drives. And then there was a change of management in those days. It was around 2000. We did this rewritable DVD, which is still kind of thing I'm pretty happy about because back in those days, people bought discs to play movies on. This is after the tape era. And what had happened was HP was like sitting on the outside of this. The guy named Josh Hogan, there were 2 factions that were a group of the DVD Forum, which was a group of Japanese companies, and there was Sony and Philips. And Sony and Philips owned most of the patents on CDs. And this other group of companies was telling Sony, look, why don't you be a country player and why don't you work with us instead of those guys at Philips and everything. But Sony basically didn't want to give up on all their intellectual property rights. And so basically there were 2 alternative ROM formats. And Josh came in and negotiated a compromise between them that actually why the DVD ROM format, the DVD movie format that was dominant for so many years is his compromise that he got them all to agree on. And within a few months, people were like putting movies on DVDs. They were not meant to be written repeatedly, right? So if you wanted a rewritable format, they all have things called edit gaps in them, which basically leave room for your timing slot. And so basically we figured out a way called high frequency wobbles to basically what I guess call turn the tracking problem sideways and actually make the timing super precise. So that's another phase lock loop problem, right? Came back again. And that led us to do this rewritable format that I thought was like really, really good and was, let's say in the early aughts was like a multi-billion-dollar business every year, that rewritable format. So it was kind of a cool thing to do. But then HP started changing what they were doing, and they basically split off the instrumentation part from the computation and printing and imaging part. And I looked around, and the part that was going to be computation and imaging wasn't going to do any computing stuff that touched the real world. And it was like, okay, I should go over and started working on instrumentation at Agilent. And so that turned out to be ups and downs, but it's been a pretty great decision overall, because HP isn't what they used to be. It's kind of, so those of us who joined when it was like this, like the engineering heaven on earth, it's tough to watch what's happened to them. It created the culture of Silicon Valley. But I kind of feel that Agilent, we've kind of restored that sense of what used to be called the HP way. And now I think Mike McMullen likes to call one Agilent culture. And it's just basically a way of basically having an open, it's what you think of when you think of Silicon Valley culture. So I basically was doing instrumentation, a lot of high speed measurement type stuff. And then there's a chance to work on atomic force microscopes. And then I worked on some interferometer stuff. And then at some point, there's another split coming, because there's always another split coming or something. Somebody's deciding that their stock isn't worth enough, and so they're going to split the company or do something. And that's how HP split off Agilent, by the way. and so that's my interpretation. I don't want to but my interpretation of it is so I ended up, being on loan to this mass spectrometry group, which is kind of ironic because my first memories of mass spectrometry are my father's an organic chemist, and I remember him going into the lab on a Saturday, and he had this big machine with a giant paper plotter thing, and these wiggly lines with humps are coming out, and he's marking these different humps with pencil notes and everything, and he's basically identifying peaks in the mass specs, right? So now we do that a little bit more automatically, but it is kind of an interesting irony that I ended up doing that. So I've been in this group for about 7 or 8 years, and yeah, you don't think of it as being control focused, but I like to think there's always opportunities to find control problems in the work. That's a very long answer to a very short question.
So I'm obviously just have been in the academic side. So I got my Ph.D. a little bit more than a year and a half ago. So I've kind of seen you through the control community conferences, and you definitely have a reputation for being involved in that community, especially considering that you're in the industry world and have been. In particular in that purview, it seems like you are always interested in doing these tutorials and these workshops that kind of get the new blood, the grad students in and seeing your view on control. So what is it about those types of talks that you really find so appealing?
Yeah, it's kind of weird because there's like multiple things that make them useful. I started with tutorials, and the first one I did, was back in ACC 2002, which was in Anchorage, Alaska. And I really didn't have something. I was between, the drive days of HP and the instrumentation days of Agilent. I didn't have anything really to talk about, but I knew about phase lock loops, and I knew that it was a control loop. It's the most ubiquitous control loop built by humans, and most control engineers know nothing about it because most of the phase lock loops folks are circuits people. And there's some really interesting things about it. It's like they don't ever worry about stability. Like we freak out thinking, is the damn thing going to be stable? And these guys are like, yeah, it's going to be stable. How do you? And so actually, that's like at the heart of a bunch of stuff. Like that, once you realize why they don't worry about it, you go, oh, okay, there's something there, right? So we can come back to that. But so I ended up organizing a tutorial session on phase lock loops and wrote this paper on a control engineer's view of phase lock loops, which was all about, if you look at the books, they all, and I have more than I need, right? I probably have somewhere between 10 and 20 phase lock loop books scattered around my office and my garage and stuff like that. And they all, chapters 1 and 2 are roughly the same. And then the rest of the chapters are whatever that writer was specialized in. So it might be for communication systems, or it might be for motor control, or it might be for something else. And the way you do phase lock loops for each of these applications is very, very different, right? The basic idea is the same, but they go off into these things. And if you're just somebody like me coming into it, you go, okay, which one do I pick for this problem? I want to buy one book and have it say, oh, you're doing this, so you should do one of these things because this is how this problem works. So I started getting that feeling when I did the tutorial paper. And then over the years, it's kind of, it's kind of repeated itself. So you kind of teach yourself a lot when you do one of these. A lot of times when you're in academia, one of the things you have to do is to get a grant, you have to like talk about this new thing you're going to do, right? And I'm kind of like, okay, well,
Mhm.
I'm doing stuff for my work, but a lot of times what I have to do is relearn what was taught, but really like make it functional. So the stuff that you learn, and you go, oh, there's all these holes there. Like that stuff I was doing at HP Labs was like, this is the stuff I learned in grad school. Why doesn't it work? And so over time, I guess just by having to write my own notes about this stuff. And here's the thing about this happens, I guess, a lot in industry is if you basically have these wonderful hand notes, handwritten and everything, and you make a copy and you give it to somebody, they go, oh, that's nice. And it'll basically like, if you put it on the computer, right, it's somehow official and people read it. It's like this magical transformation that happens because the same intellectual content was like now typeset. So I ended up with, I would do that. And
Mhm.
then at some point it would go, oh, that might be a tutorial or something. And we did stuff when I learned, when I did the AFM stuff, I relearned for like the third or fourth time PID controllers. And by the time I started like really trying to get myself into how do you like really tune a PID controller so that you do loop shaping with it, I kind of realized there was kind of that was
Mhm.
like a missing element. So that turned into a tutorial at ACC 2016, which was an Applications Friday tutorial. And those turned into our workshop, our practical methods workshop, over time. But I kind of think that there's a lot of stuff that, here, there's this a great old movie I love, Blazing Saddles. And in this movie, Blazing Saddles, there's this point where this old woman who said something really terribly offensive to the sheriff comes back and apologizes, brings him an apple pie and apologizes for what she said and
Mhm.
thanks him profusely, blah, blah, blah. And then comes back a few seconds later and says, of course, you'll have the good graces not to tell anyone I spoke to you. and so the thing about that I like about, if you're going to go for a workshop, you actually have to sign up for it and pay, right? And so you acknowledge that, oh, there's something I don't know about.
Mhm.
But when someone comes to a tutorial, they just have to walk in the room. And so I find that tutorials are like, have that little element of course, you'll have the good graces not to tell anyone that I spoke to you and I didn't know about this subject. People can come in and learn about it. So I think it's attractive to people.
Right.
We end up seeing a lot of people in the tutorials that you thought, oh well, they're teaching this stuff. They must know it, but it's cool. It's fun to do, and it seems like it fills a niche, right? That people are hungry to like hear it in a practical way and figure out how they can use stuff. So all of those things are like kind of play into it.
It's definitely a good contribution and a good pillar to our community because young researchers who are just starting out in grad school, wrapping up, or even young faculty, just having that opportunity to be like, okay, yeah, now this is my first time teaching control, and I have it 80% down, but now
Yeah.
I'm teaching it. I need it to be 99%. Like it needs to be so much closer. Those outlets and those avenues to really reinforce that knowledge or think of it in that different way. I think they can be underappreciated for the more senior faculty, but it's always I always recommend to new grad students, yeah, go do a Danny talk. You're going to think about this stuff in a different way.
Yeah, that's really great. I mean, that's great to hear that. I think that, one of the things when I was an undergraduate, I took both classical control and digital control. And I can remember those were among my two least favorite courses that I took, right? And
Oh wow.
and so and then I think E&M I thought was more inscrutable, right? E&M might have been more inscrutable, but the controls classes, and you try to think about why that is, and that there's a lot of especially if you're doing it in a quarter. There's basically, okay, there's this first week we introduce the concept of feedback and say how it reduces sensitivity. Week 2 we're doing Ruth Hurwitz. Week 3 we do root locus. It sounds like Ruth Hurwitz, but it's not the same thing. And at some point, oh, maybe we do frequency response, right?
Hmm.
And maybe we introduce state space. And the thing about that is Gene Franklin used to say these are all like different ways of looking at the same problem, right? What I found was
Right.
if you could take a step back and say, well, again, the same thing. When do I use which one of these tools, right? It's not like, there's the Maslow's hammer, which is like, if all you have is a hammer, everything looks like a nail, right? Every problem looks like a nail. The
Right.
thing
Yeah.
about, like Ruth Hurwitz is, okay, if someone hands you a denominator polynomial and it's in a polynomial form, it's been multiplied out, then Ruth Hurwitz is a really good way to check to see if it's stable. That's what you can do. And if it's somehow it's got,
Right.
it's in algebraic form and you have symbol ends, you might actually be able to tell something about, okay, the symbol, here are the limits of that, right? with locus is another way of looking at this the system when somebody hands it to you and it's factored, right? And okay, right then you could tell the students, okay, one of them's polynomial form, one of them's factored, right? And they're all about, they all stem from a
Hmm.
time when we didn't have good computers or any computers, and people were trying to figure out when does that denominator polynomial get to be zero, right? And so I think that
Right.
the context is often missing, and that's kind of what I'm trying to get to because and
Sure.
now like I have to like actively remember that I didn't like this stuff when I was an undergrad, and part of that is I think a lot of times people are so rushed to get through all the material that needs to be there for accreditation, but people often get so much involved in trying to get through like the stuff that's in the accredited material that there's not enough context, I think. And the poor students, I had this experience, which is sort of, again, I go off on
Hmm.
tangents, but in 2019, I talked to 3 different recent graduates and that had taken their undergraduate controls class. One of them was a mechanical engineer. One of them was a double E whose specialization was control systems. One's a chemical engineer. And they had almost the exact same experience and did not enjoy it. And it was kind of like, okay, this is enough of a set, spanning set for me to understand. Is we're not giving them context. And one of them said, I think it was double E said, yeah, we got to tune some PIDs at the end, but didn't really understand how that was working. And it's like, okay, if that's
Hmm.
this dude's experience, and
Right.
he was clever. He basically did a minor in software and got a job at Google, right? So he's like
Hmm.
bright enough to get a job at Google. But I think that there's
Sure.
a lot to be said for giving people context so they can use it when they're out of school. And I'm not sure exactly how to do this. This is a point of debate for with the academic crowd as well. There's and IPAC has a education committee and all, and people are doing all sorts of stuff trying to flip the classroom and do all this kind of stuff. But part of what I think is those are a lot of the tools, and I kind of sometimes feel like we really need to give people the context of when do you want to use. I
Right.
remember talking about frequency domain with chemical engineers, and they like look at you and Richard Bratz told me, he said, yeah, they're just going to give you blank stares, dude. And it was because, and if you look at it, well, okay, their time constants are in minutes. So if basically if you're going to do a frequency response function or something like that to make a measurement, you may be pulling a retirement check before it's done, right? It's just yeah, and
Exactly.
by the
Yeah.
way, if it's a chemical thing that you were trying to get, trying to do something with, how do you inject a sine wave into a chemical, and why would you ever do that and not know how to
Yeah.
deal with the pollutants that come out of that thing? So there's a whole lot of that kind of stuff, and how do you make your measurements? And yeah, I think it's still trying to give people context. And I guess when I write it up so that I can understand it, it's usually simple enough so other people can understand it. So
Yeah, sometimes that's the clearest audience is like, okay, this finally makes sense
yeah,
to me. So
yeah,
now
yeah,
let
yeah.
me
Yeah,
pass
the
on all of that
algebraic
hard
pain
work
and
to
suffering
to
is,
somebody else.
it's
Exactly, yeah. So I guess kind of flipping back to more of today's stuff.
yeah.
Are there any interesting problems? I know you're in mass spec now, but I'm sure you're still dealing with dynamics and control in some aspects. So is there anything interesting that you're currently working on?
So I think that there's a lot of opportunity. I mean, one of the things that, one of the things that I think is it's not part of my day job right now, but because of the time in the AFM stuff I worked on, first I learned how to do PIDs, and I learned how to not to think of PIDs as a separate thing from an advanced controller, right? Instead it's you do a PID to handle the baseband stuff, and then you put on these filters and everything to handle. And if you strap those together, you have like a modern high order controller, and you can do that in state space. But there's advantages to PID. So
Right.
really internalizing that I think has been really useful. One of the things that you can have is, in PID, you have integral control. And if you have integral control and you have saturation in your system, then it's really good to have anti-wind up, right? With a PID, that's like that integrator is sitting right there. It's isolated on its own. Whereas if you have this polynomial form controller, you go, I don't know, where do I put the anti-wind up, right? And so I think there's some advantages to that decomposition. And then along the lines, I ended up wanting to do low latency filtering, which led to the multi-notch. And then and I always tell the story. Eric Johnstone, who's an engineer now at Keysight, but we were all Agilent before, is working on interferometry problems. And he walks into my office one day. He says, "I want to do a Kalman filter." And I just looked at him and said, "Isn't your life miserable enough already?" Right? And he was just like, no, and he convinced me that he needed this. And so I was trying to figure out, because I just figured the thing what he was working on, it was so lightly damped, so many resonances and anti-resonance would be numerically unstable. But I also knew that the multi-notch worked super well. And so we came up with what I call the biquad state
Mhm.
space, which was a state space version of that. And then through some like accident between myself and the attorney
Mhm.
who was writing up the patent, one of us wrote down S instead of Z. And it was like, why would you do that, right? Why would you ever need because in Z you gets numerically unstable, but in S it's kind of numerically stable. Well, it isn't if you actually look at the size of, if you have fixed point computation, then you can get yourself into trouble really
Mhm.
fast. But then what happened was I ended up,
Sure.
like there's that NPR feature where they say can't let it go. I couldn't let it go. So I ended up doing the continuous time version of that. And then I realized that taken two at a time, the outputs of the states of the two different forms, continuous and discrete, mapped onto each other. So then I got kind of excited because it's like continuous time state space, discrete time state space, and they correspond to each other, which isn't very common. And so then I, ended up, there were some pieces that I didn't have for like the rigid body stuff. I got those to work. And then, so the thing that happened then was, and this relates to this year's ACC, is I sent, something to Abbas Amami, and he comes back and he says, well, the only right way to do discretization is the zero order hold equivalent. And it is. It's the exact way to do stuff under certain conditions. But I was like, really? Because basically all this other stuff is based on discretizing a block at a time. And so that this year's ACC thing is about getting to evaluating how much you lose if you do one block at a time versus the all at once thing. And it turns out that, okay, spoiler alert, you don't lose that much. Right.
Mhm.
And so you can actually think, okay, I can debug this thing, right? I can
Hmm.
actually have a state space, discrete time state space I can debug. And I didn't lose that much and the paper that this here talk is about, okay, how do you know if how much you're losing? And there's a really simple way to compare them and everything. And then you can say, look, if it doesn't make that much of a difference, use the one you can debug, right? Maybe I'm trying to make
Right.
state space great again. It's like maybe that phrase has been ruined for all time. I don't. So, but I wanted to make it usable. One of the things that, that with Eric is, so I don't do that, like that kind of stuff is in my background that, ruins quite a few weekends and evenings. But along the other thing has been, when you do stuff on mass spec, what we end up doing a lot of is, there's a lot of cases where there are PID like things on there. And when you do PID on process systems, they're very different than doing PIDs on electromechanical systems. And the way people think of them is dramatically different. And you kind of go, okay, well,
Mhm.
should be the same thing. And so actually trying to navigate between those two worlds and actually put them into one language has been kind of a thing I've been trying to do more recently, is to say, look, if you're here, this is what you do because
Mhm.
of this reason. If you're here, you do this because of this reason. But you're kind of trying to do the same thing no matter what. Right? And so have people actually a
Right.
little bit
Yeah.
more speaking a common
Yeah.
language again with that.
What do you think the major challenges are for, I guess, taking PID and pushing it towards that
Yeah.
more advanced control, what we're kind of excited about on the daily, the weekly, or maybe we don't. Maybe it's fine if we stick with PID and have that as the base standard.
So I think a lot of PID is not well tuned, right? So I
Mhm.
think the way a lot of people do PID, one of the things I had this question years ago. I gave a talk. I got invited. Mustafa Kamash, who I didn't know at the time, invited me to come down to UC Santa Barbara, which was 6 years before my oldest son would go there for engineering.
Mhm.
So I knew nothing about UCSB, but Mustafa asked me to come down and give a talk, and I had a few talks in the can. I said, sure, here's what I have. And no sooner did I say yes than Carl Ostrom sends me an email, great, you can give a talk at my advanced controls class. And it's like, and I'm like, oh gosh, now I have to like think of something new and useful. So I did this talk, right? And there's a student, he's sitting there, he's like 2 feet away from me. And the more I talk, the more pissed that guy looks, right? And I'm like, and I'm like, what did I do to this guy, right? And at the end, he's like he raises his hand. First question, right? He goes, so you're telling us all this state space we've been learning all these years is useless? And it's like, oh, jeez. think, think of something, get yourself out of this. And so I'm like slowly going, well, state-based control is model-based control, right? And he goes, yeah. And it's like, and to do model-based control, you need a good model, right? And he goes, yeah. And it's okay, old reference. But at this point where Bluto in Animal House says, "Was it over when the Germans bombed Pearl Harbor?" And they say, "Forget it, he's rolling." I was rolling at that point. And so my last thing is like, okay, well, most of the time your models suck, right? And that's the problem. And
Mhm.
he had basically taken me through this to this place, which was actually the truth is oftentimes we try to do all this advanced fancy stuff. And it's great when somebody gives you the model, right? It says, oh, the third order system, blah, blah, blah. But how did you
Hmm.
get to that? Well,
Yeah.
you had to make some measurements and that describe reality. Are you able to make frequency response measurements? Does time domain ID work? Do you do step response? Is that all you got, available?
Hmm.
And understanding what measurements you can make and what models, parameters you can tune from that tells you what you can do in reality. I thought that a lot of people were disconnected from that, because it's so easy. Everyone wants to build, have the next great algorithm. And you say, even like if you look at Kalman filtering, assumes that you have a perfect model.
Right.
All these things. And so it's like, okay, what happens when that's off? How much what is the sensitivity? And this is something I doubt I'll get to do it, but it would be great if one of my friends had a bright grad student who did this and I could work with it'd be interesting to see if you had a bipod state space where the model is much more modal and stuff like that and more close to physical parameters where you could basically say, well, what's the sensitivity of, say, a Kalman filter when I move one of these parameters by this amount? You do that
Hmm.
study. So I think that a lot of, getting back to your question about PIDs, a lot of PIDs aren't tuned that well. And our first step for the people who are like stuck tuning PIDs that, somebody else built, they basically came into this job, they inherited it. Someone says, these are the PID parameters. And you go, where's the documentation? And they look at you like, documentation? And maybe it's in the code, but this person believed that good code is self-documenting because there are people who like follow that philosophy.
Hmm.
It's not, by the way. It's just like, it's not. So basically, this person is, they don't even have the measurement tools in place. So before you do all this other stuff, you want this set of measurement tools that allows you to evaluate, okay, what did I just do? So in the stuff that we did, with heaters and everything, we spent a few months writing the code to be able to do the measurements. And then I went in and made the measurements on these heater problems in the morning, went back to my desk, was in MATLAB, derived the time constants and everything, and I had the equations to turn that into a PID, went back into the lab and jammed this in, the PID worked. And, the guy was trying to work with, what, you mean it worked on the first try? I said, yeah. And he goes, how's that? And I said, no, look, it's all this tool building that we did ahead of time that allowed it to
Hmm.
work on the first time. It's because we could make the measurements, we could do all this stuff. So I think that one of the things that we're missing is this tie into what measurements we can make, how can we tie it to the everyday problems that people are going to see. And if we can do that, then PID just becomes a part of this overall control system. It's not
Hmm.
the whole thing. You could basically do a state space controller that was really a PID and filters if you
Right.
wanted to. And so then the question, but all of this stuff comes down to how well am I modeling my system? If I'm modeling my system super well, if I have a really tight fit, then yeah, things are going to work super well because I'm not going to put a notch in the wrong place, effective when I do this
Hmm.
stuff. And so I think part of what I want to get people to is not think of it as, oh, it's either PID or advanced control. It's more like, this is a continuation, right? You get
Hmm.
this part that deals with one of the things I only understood when we did the workshop was if you have a second order linear system, a PID can control almost any second order linear system, right?
Hmm.
You really don't need anything else.
Right.
I mean, sure, you might add something else. So basically, if you think of it as, okay, I have this rigid body part of the problem and I have this other part of the problem, and I'm going to think about it as the PID is doing this and think about one of the things that the phase lock loop engineers do is I had this Rick Carlquist, who is this really sharp phase lock loop engineer, worked at HP and Agilent. I met him at Agilent, and I remember looking at some of his circuit diagrams for phase lock loops, and I'm like, see, oh, you got a notch filter here, and you got this other thing. He says, yeah, that's for the 2x, and that's for this and that thing. I said, this is like a 10th order system here, and he says
Right.
that's never in the PLO books, and he goes, yeah, it's never in there because no circuit engineer, no RF engineer worth their salt would not know that you had to put that into the circuit. So what they did is they took this high order problem with all these 2x
Hmm.
frequencies and 10x and all harmonics, and they beat it into a second order problem. And they go, look, I can do this really simple controller here. And it's like, and
Right.
so you think about that and you go, well, maybe we can think of it that way. Maybe we can beat these problems into these simpler versions
Right.
of themselves. And then we can say, and if you can break it up that way, I think it's often more approachable to people rather than this, oh no, throw away everything you've been doing that works and do this
Hmm.
new thing, which by the way, we don't have good measurements, so your model's going to be terrible. And oh, you didn't
Right.
get it to work right. Well, it's not that the method is bad, it's that there's this model mismatch. So
Hmm.
anyway, I think that that's what I would like to get people to view it as not an XOR, but as a continuum. And you do this one set of things that work
Right.
really well, and then you make and in order to talk to people in industry, I think the first thing you do is you show them you can understand their problem and make their PID better.
Hmm.
Because if you make their PID better, if you show them how they can improve their PID, show them how they improve their filtering, and everything like that, how they improve their measurements, you got some street cred with them now.
Right.
Basically, you didn't come in and just talk over their heads. You understood their problem and you fixed something, right? And you showed them
Hmm.
how to do it. So I think that that's what I feel is an effective way to get more people, to enjoy doing control. It's kind of where I'm at now. I like doing control, right? It's not me as an undergraduate.
Yeah, and like you said, if you can tie that all back to, PID being this, super powerful tool that can, given this nice, well-tailored problem, is going to be more than effective at what you're trying to do. How do we get real world problems to then fit into that window? I think it makes it like, okay, then classic control makes sense. Like, that was a meaningful class
Yeah, yeah.
now.
And so I think that there's the most common adaptive algorithm in the world is LMS with the Woodrow and Hoff. And when Bernie describes it, he's one of my mentors and he's still around, and I just love the guy. He's the only person who calls me kiddo, and it's like it's like, okay, it's nice to have somebody who still like thinks of you as a kid, right? LMS is by far the most utilized adaptive algorithm. There are faster algorithms, and if you ask Bernie, he'll say,
Mhm.
"Yeah, they're faster algorithms." But you know what? People can debug, can understand what LMS is doing, and they can debug it. They can program it, so it means they can use it. And if you go in there and say, "Well, you need
Mhm.
a conjugate gradient," why don't you instead say, "Okay, this builds on what you're doing, and
Mhm.
if you think about it this way, this is now taking that part of the problem and is giving you a little bit of better directions to search." So it's not an
Mhm.
either or thing. And yeah, I mean, you can see LMS algorithms all over the place, right?
Oh yeah, they're ubiquitous everywhere.
And so I think it's the same kind of thing. It's not either or, it's this is a starting point and we show how to make this really well and do work really well. When I've done adaptive stuff and it hasn't been as much as I would have liked, the times I've done it, I've isolated the parameters so that by the time the LMS gets turned on, it's so absurdly fast. It's like you go, okay, I'm not sure why I would do anything else because that wasn't the hard part, right? The hard
Right.
part was isolating the parameters down to,
Mhm.
getting it so that the prediction error was really tightly coupled to the parameter error. And once you did that, it was like, it
Mhm.
doesn't really matter what you're doing, right? You could do any one of these things.
Okay. No, that's very insightful. Yeah. So what's on the horizon for you? We're in 2024 now. There's got to be something coming up for Danny.
Well, I mean, I'm curious to see how that discretization thing will go because that's to me I'm still trying to get. I really wanted to get people into this mindset that look, if you take this biquad based approach and discretize one at a time, then you can make this very physically relevant state space type thing. I would really like both because I think it works, but also from a personal satisfaction. I would like to see that get adapted. So I'm curious to see if bring in this last bit of discretization thing that says, look, it's okay to discretize things one block at a time. You don't lose that much, but you
Hmm.
can check if I can make that case, if that makes so that's like ACC 2024. I also
Okay.
get to go to Almeria for IFAC Advances in PID and give a plenary talk there. So what I'm trying to, kind of, as you might have gotten, I find myself, all of a sudden an expert in PID, and it's not a place I expected to be in 15 years ago. My theme is going to be like this unexpected expertise. And you look at it coming from a mechatronics perspective and trying to fuse in the chemical process, kind of the process world view of things and see what the commonalities and sort of like, again, I'd like to get us talking a same language on this kind of stuff. So that's my goal for that
Right.
talk. And then there's education stuff, that I'm involved with, outreach to high school students with the A squared C squared education committee. So we're having some
Okay.
success with that, especially at the MEC conferences, which happens during the school year. So it's really great when
Okay.
you can do that outreach. We got to get this material online because even if, no matter where we go, we're only getting there at most once every 9 years. And so we're not, our duty cycle with students isn't high enough. So we have to find a way to use these
Right.
live sessions to feed material online that's compelling and usable by students and teachers to get a basic idea. They don't
Hmm.
have to become control engineers, but systems that depend upon feedback are going to be much more ubiquitous, in the coming years than they have been. And people they're going to be very visible. When a little igloo cooler with with wheels comes up and drops off your dinner, thing. Well, that was only possible because of feedback, right? And people need to understand how that enables their world, even if they don't do it right. It would be good for the world to kind
Right.
of understand this is what feedback is. Here are the limitations it places on you. And so I really, that's kind of a thing that we're trying to get to in the education committee as well. And
Mhm.
appreciate you helping, by the way, with the MEC and the student workshop, because that was, I have videos of that and I haven't transcribed them, but that was by far, I think, the most successful one we've ever done. So
No, it was a pleasure. I was so glad that I was able to do that in sunny Lake Tahoe. Although I can't remember how sunny it
yeah,
was there in
well,
October,
that's
but
okay. Yeah. That's, by the way, that's, if you, my background, if you're looking at that, we went right by that island. That's Emerald Bay.
oh yeah, I recognize so I was Reno born and raised, so Lake Tahoe is my lake for sure. Awesome. Well, thank you so much for taking the time to sit
Right.
with me, Danny. This has been wonderful to
Yeah,
chat with
great.
you.
Thank you so much.
And I'm not sure where I'll see you next, but I
Yeah,
hopefully will be
likewise.
soon.
Maybe ACC for sure. If not,
Wonderful. Yeah. Yeah, I'm gonna do my best to make it out there. All
thank
right.
you.
Thanks, Danny.